So I'm Oded, I'm co-founder and CEO of Dragonfly. We also have here Roman Gershman, who's the CTO and co-founder of Dragonfly, and the original creator of the Dragonfly project. Obviously, we call him Father of Dragons. Hopefully you ate good, and now you're ready to talk about or to embark with me on a journey throughout the evolution of in-memory data stores. It's a story that mirrors the growth of the internet itself, a story of architectural choices and the constant tension between hardware capabilities and software design. Does it work? It works. So we'll begin our journey at the beginning of the millennial. This was the first time that companies had more than 100,000 users online, like online users. Really traditional databases using magnetic tapes were too slow and could not scale to accommodate the throughput that were required. Until that in 2003, Memcached came. In the context of today's complex systems, Memcached seems remarkably simple, and it was. It was a distributed key-value caching system designed to solve one problem and one problem only. The immense performance gap between reading data from memory versus reading data from a spinning hard drive. The difference is staggering. On average, reading data from memory takes about 100 nanoseconds, while even the fastest disk would be 1,000, if not 10,000 times slower. By providing a pool of memory to cache database query results and other hot data, Memcached was a critical enabler for the first wave of massive internet scale applications. It helped fuel the growth of sites like Facebook, YouTube, Wikipedia, allowing them to scale their performance by dramatically reducing the load on their backend databases. This was the first great leap, moving data from disk to RAM. The second era is characterized mostly by the vast adoption of smartphones. Having millions of online users was not a unique trait of a few big companies. Now, it's not only early adopters of in-memory data stores. Now everybody needs it. And everybody was choosing Redis. Redis represented a profound architectural shift. It wasn't merely a cache. It was an in-memory data structure store. By providing powerful server-side atomic operations on rich data types like sets, sorted sets, hashes, Redis empowered developers to do something transformative. They could move application state out of the compute layer and into a shared and persistent data layer. So Redis was actually the key that unlocked the era of stateless applications. As we all know, scaling stateless application is pretty simple. You can spin up and down compute instances without worrying about session data or local state, because the state lives in Redis. This separation of concern became a fundamental pattern for modern distributed systems. When Redis was first created, we as humankind produced around 1 zettabyte of data every year. Fast forward 15 years, we are now producing around 180 zettabytes of data this year. So it's like a 2 orders of magnitude jump. Hardware has evolved significantly to match this growth. Amazon launched in 2006 an EC2 instance with 1 core and 1.7 gigabyte of memory. Almost 2 decades later, modern hardware is completely unrecognizable, with modern cloud servers boosting 2 orders of magnitude more CPU and 3 orders of magnitude more memory. We've transitioned from a single core into cloud instances that are now packed with 128 cores, and from 1 gigabyte of memory to 1 terabyte of memory. Yet during this explosive data growth and hardware evolution, the fundamental architecture of the dominant in-memory open source, Redis, has remained largely unchanged. It was designed for the data loads of 2009 and still mostly operates within that paradigm with a single core architecture. With a single core architecture, the only way for you to scale is basically to scale horizontally. Let's explore horizontal scaling challenges that are often misunderstood. Hotspots. Many systems are designed with a convenient but flawed assumption that workload traffic is uniformly distributed. In reality, however, virtually all real-world systems follow a skew distribution, often described by the Pareto principle or the 80-20 rule, where a small fraction of the items account for a large majority of the traffic. So imagine a football stadium with 100,000 seats, and the game starts in like 30 minutes. So we open 100 gates, expecting 1,000 people to queue in each gate. But in reality, the busiest gate would have something around 2,500 people, while the less busy one will have around 600 people. This phenomenal distribution is called Zipf distribution. This power law distribution applies to web traffic, social media posts, popularity, and most importantly for this conversation, database key access patterns. So in database terms, provisioning 100 shards, assuming uniform traffic, but with Zipf reality, means that a few hot shards will take a load 4 times more, or in the previous lecture it was 6 times more, than they can actually can handle. So latency will spike, requests will drop, and horizontal scaling will not help, because if we will add more shards, the same people will still queue on the same hot gates. Under the same distribution, if we will build only 10 gates, but beefier gates, the busiest one will have 11,000 people, and the less active one will have 9,000. So the gap would be now not 4 or 6, it will be around 20%. Much easier to handle. Which brings us to today's workloads. Today workloads demand more from in-memory solutions. While in-memory technology traditionally cache your database and store your application state, a new generation of workloads require even greater capabilities. In-memory technology has recently evolved into content store that powers smart applications. A prime example is cybersecurity, where evaluating the risk of an incoming transaction requires considering the current session context, the IP history, and hundreds of other parameters. The more context available, the more accurate the decision would be. The process is integral to all modern applications, including advertising, e-commerce, fintech, gaming, or any other vertical. The concept of context is pivotal to harness the power of AI. Last week, Claude incorporated memory into their service, following similar implementation by Google and OpenAI just a few months prior to that. Context is not limited to a single session or to past session history. It can be shared context across sessions, or shared across teams, or shared across the entire company. Furthermore, context is not static. It is live, it's dynamic. It constantly needs to be updated and refined. Those advanced content stores typically necessitate much higher or much significant data volumes and throughputs than traditional workloads that we know or that we used to know. Let's explore some of the available solutions that we have in the market. So in 2004, in a response to the license change by Redis, the open source community forked Redis into Valky. Backed by major companies like Google, AWS, and Oracle, Valky aims to be the open source development branch of Redis. However, Valky is an evolution, not a revolution. It inherits the same fundamental single-threaded architecture of Redis. The most significant enhancement of Valky is the introduction of I/O threading. This is a valuable optimization that offloads the tasks of reading data from the network and writing data to the network to a pool of helper threads. This frees out the main event loop or the main thread to execute commands, which can lead to substantial throughput gains, especially for workloads with many small, simple get and set requests. But this is a compromise, not a solution to the single core bottleneck. You can scale the I/O capacity by adding more threads, but the data processing capability is fixed. For any CPU-intensive work, like adding items to sorted sets or running heavy Lua scripting, the main thread becomes bottlenecked, and the entire system, including the I/O threads, must wait for that single thread operation to complete. The system performance is ultimately dictated by the speed of that single core. Which brings us to Dragonfly. Dragonfly was designed from the ground up to solve this fundamental bottleneck. It reimagines the in-memory architecture from multi-core world by applying share nothing principle within the same process. The entire in-memory dataset is partitioned into a number of shards, where each shard is exclusively owned and managed by a single dedicated CPU core or CPU thread. When a request arrives, it is routed directly to the thread that owns the key it targets. This design provides true parallelism for data operations. Within each of those threads, Dragonfly employs a sophisticated asynchronous execution model. It uses a scheduler that manages thousands of lightweight execution contexts called fibers. This creates a fully asynchronous execution on a per-thread basis, similar to Node.js and async Python. Any potential long-running operation, such as writing data to disk, is wrapped in a fiber. So while one context is blocked on I/O, other contexts on the same thread can continue running. This results in a system that remains highly responsive even under very heavy workloads. Finally, while a single Dragonfly instance can scale to handle terabyte of memory and millions of requests per second, it also offers a cluster mode for workloads that exceed the capacity of a single machine. And unlike Redis and Valky that are using the Redis protocol, the Gossip protocol that was also mentioned here before for orchestration, Dragonfly utilizes a centralized orchestration layer to perform all those clustering machine orchestration, saving a lot of end-to-end communication in between the shards and allowing Dragonfly to scale to much higher workloads than Redis and Valky. Modern context memory workloads demand 10 times the throughput of traditional in-memory workloads. I've demonstrated that vertical scaling alone is insufficient to meet those demands. Valky attempts to address those challenges with I/O threading, enabling sublinear scaling. But it remains constrained by the single core event loop. In contrast, Dragonfly multi-threaded share-nothing architecture scale almost linearly with the number of available CPU cores. Public benchmark consistently show Dragonfly achieving millions of operations per second on every single node. Going back to the example of the football stadium, when less gates are being used, less provisioning is required, and less waste is being produced. This immediate consequence are extreme scalability, management simplification, and reduced total cost of ownership. One of the biggest challenges facing in-memory system is the growing disparity between data size and the cost of RAM. While memory is cheaper than ever, modern data are growing even faster, and storing multiple terabytes entirely in RAM can be very expensive. To address this, Dragonfly is introduced an SSD data tiering feature. This is not simply a disk-based cache. It's an intelligent mechanism that extends a single instance effective capacity by a factor of 5 while maintaining sub-millisecond latency. It works by offloading only the large string to a fast local attached NVMe storage. All keys and all other smaller values and complex data structures remains in RAM for the fastest possible access. When an offloaded value is required, it is seemingly fetched from the SSD back into memory. This entire process is powered by a highly efficient I/O Uring API, minimizing performance impact. This feature transformed Dragonfly from a pure in-memory data store into a hybrid memory storage system, making it economically viable for much larger data sets than traditional solutions. To complete the puzzle, modern in-memory workloads requires infrastructure that can scale vertically as well as horizontally, scale data beyond memory, and on top of all that, all major in-memory solutions in the last 2 years added advanced search API to support vector and JSON search. Some do it better than others. To conclude, in 2010, companies won because of the speed they can access data. In 2020, companies won because of greater velocity moving data around and delivering features. In 2020, companies would win because they can harness huge amounts of context data in real time to deliver fast and smart applications.
So that's a really interesting thing that, going to local NVMe SSD. Doesn't that now place you not just versus Redis, but maybe against key value systems like an Aerospike?
So Aerospike is also like a durable storage. Dragonfly currently offloads data into the SSD, but it's still predominantly like the keys are still in memory. So basically, you can think of it and use it maybe like that, but it depends really on your workload. If you have to have durability, so it's not the right solution for you.
Fair enough.
But can you still rehydrate the cache from NVMe?
I'm sorry?
Can you still rehydrate the cache from the data in the NVMe?
So let's say that, I don't know if it works, yes. So let's say that you lose the instance and you lose the key table, you will not be able to take it from NVMe and load it back to the to memory.
Okay, and then I did have a separate question. When you talked about the challenges of horizontal scaling, you highlighted hotspotting. How does Dragonfly Swarm handle hotkeys?
So maybe we can have Roman to answer part of it, but I just demonstrated that vertical scaling solve most of the problem. Because the problem of hotkeys, basically, when you work with Redis slots, and you have like a few hot slots that are on the same machine, basically, you need to have every machine that would be provisioned to be more provisioned so you will not, the entire cluster will not fail. When your infrastructure is vertically scalable and those machines anyways can handle a lot of load, so then the distribution basically become more uniform than with 100 shards. So it solves most of the problem, but of course, if you have a single key that takes 10 million requests per second, this is not a solution for it.
Right, thanks.
You want to add something, Roman? You want to ask me a question for my best boy? Something? No. Thank you very much.